All right, let's take a look. So again, when you're given a table like this, it could have more than 3 entries or so, but we do want to kind of maybe use that formula we used before, which is basically kind of the rate 2 over rate 1 equals basically our 2 sort of entries into the table. And again, we're looking to choose 2 entries where one of them stays the same in terms of their concentration, the other one varies. So just looking at it, we can see 1 and 2 will keep our S2O8 constant and will vary our other reactant. Our generic rate law would be, again, just our reactant. So our K S2O8 2 minus to the X and our I minus here to the Y. So looking at experiments 1 and 2, we can, again here, I'm going to kind of choose the larger rate to put up on top so I get a little bit more of whole numbers. So I'm going to put everything from experiment 1 up on top. So that's going to be 2.2 times 10 to the minus 4 equals our K 0.08 to the X and 0.034 to the Y. I'm then going to put everything from experiment 2 on the bottom. Gives me 1.1 times 10 to the minus 4, our K 0.08 and our 0.017 to the Y. At this point, we'll do our division. That's going to give us a 2. Once again, the rate constant should be the same number on top and bottom, so they will completely cancel. And again, our order here should be the same on top and bottom, which means that this guy would also completely cancel. And that leaves us over here a 2 to the Y. Once again, you could probably visually see this one. Y in this case is going to equal 1. But once again, if you don't have maybe a pretty whole number on each side, the natural log of both sides and divide it out will get you there. Any questions on that part so far? So basically what we just figured out was the order with respect to I minus is 1. We're now going to try to figure out the order of S2O8 by going back to our table. And in this case, we actually want to keep the I minus constant, which happens here in experiments 2 and 3 that will take place. And we'll do the same thing. So looking at experiments 2 and 3, I'm going to take the larger rate, which is experiment 4, and put it up on top. So that's going to give me 4.4 times 10 to the minus 4 equals my K, and 0.16 to the X, 0.17 to the Y. Everything from experiment number 2 will go on the bottom. 1.1 times 10 to the minus 4. K 0.08 to the X and 0.17 to the Y. Dividing it out gives me a 4. Once again, the K should completely cancel. The Y here, as we just figured out, is 1, will also completely cancel. And here that will leave us then a 2 to the X in this case when we divide that up. In this case, X should equal 2 in this case. And again, you can take the natural log of 4 divided by the natural log of 2 will get you 2 as well if you needed to. Any questions on that? That tells us that the order with respect to our first guy here is actually A2. That will give us our completed rate law with our orders. So that would give us really a rate law that looks something like rate is equal to K times the concentration of S2O8 2 minus, and that was 2 squared times I minus here. The overall order of this reaction would be 2 plus 1, which means this would be technically a third order reaction. Any questions on that there? Once we have gotten the orders and the completed rate law, now you can go back to the table and use your completed rate law to actually solve for the value of K in this case. And you can choose any entry in the table. It should give you the same K value. So it doesn't matter if you choose experiment 1, 2, or 3, as long as obviously you keep the numbers together that go with those experiments. So here, just to mix it up, why not? We'll do experiment 2's information. And using experiment 2's information, rearranging my rate law K would equal the rate divided by S2082 minus. Again, I do need to square it times the I minus. That is going to give us the numbers if we put it in from experiment 2, 1.1 times 10 to minus 4 molar seconds divided by our 0.08 molar squared times 0.017 to the Y. Guess I forgot a 0 on that, but it didn't make a difference. There you go. And if we put that, that's not Y, but that's actually 1 in this case. So we'll put that in there, 1.1 to the minus 4 divided by 0.08 squared and divided by 0.017 to the first power gives us a 1.01. Units here will actually be, because there's molarity there, molarity and molarity will cancel, and that will leave us 1 over molar squared seconds as the units. As you can see, those have different units than the second order one that we saw, and also the first order one has different units as well. Any questions on that? And once again, if you just look at the units, up on top you had molar seconds, on the bottom molarity was squared and molarity. Again, those cancel, leaving you with 1 over molar squared seconds. And like I said before, I had a typo without the 0 there, but it didn't matter in that particular case. Any questions on that one there? So this is a much larger rate constant, which means that perhaps this reaction would occur perhaps a little quicker than maybe some of the other ones. All right, let's try one more here and see. I don't think you have that one, so we'll do, I think this is the one you have. So let's see this one, same thing, figure out the rate law, the orders, the overall order of the reaction, and the value of the rate constant. Okay, let's take a look. So once again, we're going to be looking for our 2 entries where we keep one of them constant, the other one varies. In this case, we have a few extra one to choose from. And again, it doesn't really matter which ones you choose. They should really all come out the same. So just looking at it, I could do experiment 1 and experiment 2, and that will keep those 2 guys constant and vary the other. So let's take a look at that there, experiment 1 and 2. Our generic sort of rate law looks like K, and again, just our reactants here. All right, so taking a look at those 2, I'm going to choose again the larger guy to put on the bottom, iron top. That will give me 32.3, and in case you missed it, it is times 10 to the minus 7 from the table there. So you want to make sure that you put it in there. If you didn't, you'd be okay at this point, but later on you'll be in some trouble if you forgot that part. 0.06 for my NH4 and 0.2 there for my other guy. Going to put all the information for the first experiment in there, 10.8 times 10 to the minus 7, my K 0.02 and my 0.2. So if we do this, our 32.3 times 10 to the minus 7 divided by 10.8 to the minus 7, going to give us basically a 2.99 is equal to these guys canceling, these guys completely canceling, and that will leave us a 3 to the X. I would say probably you could round that up to a 3, and you would be able to see that X is equal to 1. If not, if you took the natural log of 2.99 divided by natural log of 3, you basically get 1.000 something. So it's pretty much 1 in terms of the X value. Any questions on that there? At this point, we would then go back to our table and choose 2 entries where we keep the NH4 plus constant, and it looks like it is 3 and 4 in this case. We'll do that. So 3 and 4 will do it for the other way. So putting my larger value up on top, 21.6 times 10 to the minus 7 equals my 0.2 to the x, and my 0.0404 to the y. Taking experiment 3 and put it on the bottom, 10.8 times 10 to the minus 7, 0.2 to the x, and 0.0202 to the y. So again, doing my division here, we're going to end up with a 2 is equal to these guys here canceling out completely, and a 2 to the y, which means y is equal to 1 in this case as well. At this point, that means that the completed rate law would be the rate is equal to K times NH4 plus or NO2 minus. Again, you don't put the ones usually. That means though the overall order here is going to be 1 plus 1, which is second order. Now that we do have the completed rate law, we can solve for K. And K in this case would be the rate divided by NH4 plus and NO2 minus. And again, in this case, since we actually have 4 to choose from, you could choose from any of the 4. It doesn't really matter. It will come out the same. So we'll just take experiment 1. This is the place where it will make a difference if you forgot this part. So you do want to make sure, again, you didn't forget it. So 10.8 times 10 to the minus 7 molar seconds divided by our 0.02 molar and our 0.2 molar in this case. Going to give us I'll give us like a 2.7 times 10, looks like the minus 4. Units here, molarity on top and bottom will cancel, and we'll be left with 1 over molar seconds, which once again is a typical unit that we see for the rate constant for a second order reaction. Any questions on how to figure out the rate law, the orders, the rate constant? You do need to know how to do that. Yes. Okay, so now that we talked about how to calculate sort of the rate law, we're going to talk about specifically specific types of overall reactions like first order, second order, and zero order reactions. These are the most common sort of reactions that you occur. Let's talk a little bit about first order first. And really the reason why when we talk about first order, second order, and sort of zero order reactions as being most common, that's because if you think about the reactions or just reactions in general, you probably know that in most cases, the number of reactants that you have are either 1 reactant or 2 reactants, occasionally 3, but it's very rare to have, multiple reactants like 4, 5, 6 reacting at once. So a lot of times, first order, second order are zero order are very common for reactants, which means if you only have 1 reactant or 2 reactant, then, a lot of times second order is kind of where you usually will top out maybe, or maybe third order. But usually 0, 1, and second order overall are really the most common types of reactions that we come across. First order reactions are really important types of reactions. They are really the ones that you see with radioactive decay. So if you take 200B and you get to the nuclear chemistry chapter, this is what you will see again. All radioactive decay follows basically first order kinetics. So these are sort of the reactions and equations that you use specifically for first order. Obviously, the way that we could get to first order is we could have a reactant that goes to our product. That would give us a rate law that is equal to K times the concentration of A. There's really a couple ways you could get there. This is probably most common in like a decomposition reaction, for example. You could have 1 reactant that has an order of 1. You could also have 2 reactants where 1 is an order of 1 and 1 is an order of 0. So that's another way that you could get to a first order overall. When we do solve the rate law for the value of K and we just look at the units, as we were talking about a little bit earlier, these are the common units that you find for a first order reaction overall. And if you are given the value of the rate constant and it has these units, you know that you're actually dealing with a first order reaction. And that is 1 over seconds or reciprocal seconds. As I mentioned earlier, although most of the time, like for example, what we're doing yesterday in the experiment are in a lot of kinetics experiments, we usually measure things in terms of seconds because we don't want to be there all day measuring, but it doesn't necessarily have to be 1/seconds. It's really 1 some unit of time. It can be minutes, hours, days, weeks, years, but most of the time you'll see it as 1/seconds because again, that's usually what time is sort of measured in a lot of experiments. When we look at that, what we would expect to happen in this type of reaction at first order is over time, the concentration of A will start to decrease. And that is what we see here as time goes, it starts to decrease. Kinetics are all about sort of graphs and really linear relationships. So we can take this rate law here for first order, and this gives us what is sometimes referred to as the integrated rate law. And that is the natural log of A is equal to the natural log of A naught minus KT. That is like your final concentration. That's like your initial concentration. K is your rate constant. And T is actually time here. So T is time, not temperature. So that is time. It is important when you use this equation that K and T are in the same units. So like I said before, you could have a rate constant where it's like 1/minutes, and you could have time of like hours. So you got to get those into the same units for everything to cancel out. Now, because the kinetics always deals with sort of linear relationships, you could rearrange this first order integrated rate law that looks something like this as minus KT plus the natural log of A naught. And that will actually give you the linear relationship that occurs, and that is the y is equal to mx plus b. That means that typically speaking, when you see a graph for a first order reaction, on the y, you graph the natural log of A. On the x, you graph the time, and that will give you a linear relationship. As we can see here, a nice linear line actually has a negative slope, red line, and you can take the slope of that line and it will equal minus k. So the slope will equal minus k. Your slope of your line will be negative, and equals minus k means negative and negative equals a positive value for your rate constant. So graphically speaking, you could use the graph and graphically figure out the value of the rate constant by taking the slope of that line through that linear relationship. There's also half-life, as we will see in a second here. And for a first order reaction, the half-life is equal to the natural log of 2 divided by the rate constant, or 0.693 divided by K. And the half-life is the time it takes for half of whatever you started with basically to go away, right? So if you started with 10, after the first half-life, you got 5. After the next half-life, you got 2.5, and so forth as you go through it. Now, a lot of times the half-life equation and the integrated rate law is used together, especially in sort of nuclear chemistry. They use it a lot together when you do it. So a couple of things that are really important when you think about a first order sort of reaction is the units of the rate constant is very important. This integrated rate law, the half-life equation, and also the typical graph that you see for a first order one is typically that linear relationship. We will actually see this graph in just a second for a different order reaction, but it is not it is a linear relationship rather than what we see here. Any questions on that there? All right, so if we take a look at this here and we wanted to figure out, we have this reaction, which is 2A goes to B as first order with A, has a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds. We want to know how long will it take for A to decrease from 0.88 to 0.14. So a couple of things is helpful here. Obviously, it tells us it's first order. If it did not tell us it's first order, it did give us the value of the rate constant, which is 2.8 times 10 to the minus 2 reciprocal seconds. And as soon as you see those units on the rate constant, you know that you are dealing with a first order reaction. So again, as I mentioned earlier, they will not, a lot of times in kinetics chapters and problems and flashing lights go, hey, it's first order. They will just give you the value of the rate constant. And from the units that you see there, you're supposed to sort of know, which one it is. So because I do know that it's first order here, that brings into play really our first order equation, which is not that without the zero on that side. I'll just get the eraser. Go. So that's going to be natural log of A naught minus KT. In this case, we have the initial concentration of A is 0.88. We have our final concentration of A, which is 0.14. And in this case, we'll put it in. So natural log of our final 0.14 equals the natural log of our initial minus our rate constant here, 2.8 times 10 to the minus 2 reciprocal seconds times time. Now, there's a couple of different relationships that you can do with the natural log, but personally, I just take the natural log of this and then take this and subtract it to the other side, basically. So we'll take the natural log of 0.14, subtract it from the natural log of 0.88. That is going to get us, let me go and try again, natural log of 0.14 minus the natural log, there we go, of 0.88. Gets us a minus 1.838279. I'll take a few digits. That will equal a negative 2.8 times 10 to the minus 2 reciprocal seconds in our time. Now all we have to do is divide this to the other side. So we're going to, bless you, we're going to divide it 2.8 to the minus 2. Going to give us a time that is about 66 seconds. So in under a minute, we will drop the concentration of this guy from 0.88 to 0.14. Any questions on that there? All right, so as I kind of showed a second ago, again, there is a half-life equation that is specific for first order, and just really substituting into the integrated rate law for the initial divided by 2, which is basically what the half-life is, gives us a natural log of 2 divided by K. So the half-life for a first order reaction is independent of the initial concentration, and that's not always the case. So in this case, if we want to know what the half-life is, and we have the rate constant given to us, we would go into our half-life equation, natural log of 2 divided by K, put it in our K, gives us the natural log of 2 divided by 5.7 times 10 to the minus 4 seconds. That will give us a natural log of 2 divided by 5.7 to the minus 4. Gives us about 1,216 seconds, or about 1,200 seconds, give or take a second or two in this case. Once again, I do know that this is first order because the units associated with the rate constant tells me it is first order. It is at 1 over reciprocal seconds. Any questions on that one there? All right, so why don't you try one here and see what you come up with. Here's just a graph, obviously, as we talked about, every half-life, you lose half. About 10 half-lives, you'll be done. All right, we have this reaction. It is first order with a rate constant 2.9 times 10 to the minus 7. Find the concentration of the SO2 Cl2 at 865 seconds when we have an initial concentration of 0.0225. So see what you come up with here. Okay, let's take a look. So once again, it's nice enough to tell us it's first order, but again, oftentimes it will not. But we do have the value of the rate constant given to us, and we do see the units. So that tells us that it is a first order reaction, and that means our K is 2.9 times 10. Scribbled on it, but I think it's -4. And that means that we should use our integrated rate law for our first order here. We are looking for the concentration of this guy at the end. We do have the initial concentration given to us, which is 0.0225. And we're going to go for a time that is 865 seconds. So at this case, we will have the natural log of A, which is what we're looking for, equals our initial concentration of 0.0225 minus our K, which is 2.90 times 10 to the minus 4 reciprocal seconds, and our 865 seconds. This is what I was talking about earlier. In this case, we are okay. These are both in the same units of seconds, but oftentimes they are not. So sometimes one's in minutes and seconds, hours, days, weeks, whatever it may be. So you want to always make sure that they are in the same unit of time so that they cancel out correctly. We basically can clean up the right-hand side here by taking the natural log of 0.0225 minus 2.9 to the minus 4 times 865. That will give us the natural log of A is equal to minus 4.045089. To get rid of the natural log on the left-hand side, you could take the E of both sides on your calculator. It's usually right above the natural log button. Take the E, basically of both sides. And when you do that, these guys basically cancel out and you end up with just A. And if you do that, you end up with something like 0.0175 molar, right? And that would be our final concentration. And we can kind of check to make sure we're okay in a sense, because it is less than what we started with, right? So if you happen to get more than what you started with, you're going in the wrong direction. Yeah, so should be decreasing with time here. And that is what we see. Any questions on that? And again, on most people's calculators, your natural log button, E to the X or something like that, that's what you want to use. Yeah. Usually I say it's a shift or second button to do that. Any question on that one there? All right, so why don't you try the next one, see what you come up with. We're looking for what is the half-life, I think. All right, so in this case, we're looking for the half-life. Once again, we could just look at the rate constant units and know that it is first order because of units, which means we would want to use the half-life equation that's associated with it, which is the natural log of 2 divided by the rate constant. That gives us natural log of 2 divided by 0.271 reciprocal seconds. That means that we will end up with about 2.56, and the units here are seconds. That is, I would say, a super fast half-life, right? Pretty fast. Every 2.5 seconds or so, half of whatever you have is gone. Yeah, so it's going super fast. Yeah. Any questions on that one there? Obviously, when you divide it out, the reciprocal seconds become seconds. Yes, on top. Question on first order. Again, the integrated rate law, this half-life reaction is used specifically for first order kinetics. And again, you will see this again in 200B when you talk about radioactive decay. It always follows basically these guys. The equations are pretty much the same. Sometimes they use different letters, but it's basically the exact same equations. Any questions on that there? Now, there are two other very common orders of reactions that we come across, which is second order and also zero order reactions. And they also do have some different sort of rate laws and equations to use. So let's take a look at second order reactions. And a second order reaction can be really achieved in one of two ways. It can be achieved obviously by a single reactant that is to the order of 2. It also could be achieved by having 2 reactants where each one is first order, right? First order and first order will give you a second order one. Again, as I mentioned before, if we kind of rearrange the rate law, which in this example would be the rates equal to K times A squared, and solve for just the units, we do hit the typical units that we associate with a second order reaction, which is different than what we see with a first order, which is 1 over seconds. This is 1 over molar seconds. Frankly, you could actually count the units and it will tell you the orders. So 1 over seconds is like 1 unit. 1 over molar seconds is like 2 letters. So that's second order. And 1 over molar squared seconds is like 3, which is like third. So you a lot of times could sort of, in most cases, sort of count the units and it'll tell you that. Not in all cases, but it's a kind of a way you could sort of figure it out. It has a integrated rate law that's a little bit different. It is actually 1 over the final concentration equals 1 over the initial concentration plus KT. These are all the same sort of things. That again is our final concentration. That's our initial. That is still our rate constant. And that is still time. It has a half-life equation where the half-life is equal to 1 over K times the concentration, initial concentration. Unlike first order, a second order reaction, half-life is dependent on how much you start with. It's dependent on the initial concentration, which is for a first order reaction is independent of the initial concentration that you have. As I mentioned before, kinetics is all about sort of linear relationships. So you can rearrange this equation of 1 over A equals KT plus 1 over A naught. And that will give you your equation for a straight line of your Y is equal to MX plus B. Again, on the Y, we would graph 1 over A, which is what we see here. On the X, we would do our time, which is what we see here. This is actually going to give you a positive sloping line there. And that means that when we solve for the slope, it actually equals the rate constant in this case. Again, typically when you solve for the rate constant, it should be a positive number. So this obviously will give us a positive number. By the way, B is the y-intercept, right? So that is where obviously it crosses the y axis there. And you could also solve for that as well in this case. So we do get this equation. So much like first order, there's a few things that are really important to remember. For second order, the units associated with K, the integrated rate law, the half-life equation, and again, the typical graph that you see for a first order, our second order reaction will give you this positive sloping line. And you can see it's obviously different than what you see for first order, which is heading in the opposite direction, kind of going down and with time. In addition to second order and first order, another very common sort of order of reactions is zero order. And zero order reactions can be achieved by having one reactant to the zero order. And as we talked about earlier, anything to the zero order is basically equal to 1. So in this particular case, when we solve for the value of the rate constant here in terms of units, using our rate law here, we see that we actually do get the same units that are basically the rate units, which is molarity over seconds. So obviously this is one where you can't count the units, it won't come out right. But any of those ones where it's 1 over something, you could kind of count the units. This has a integrated rate law, which looks just like the first order one, except there is no natural log happening here. So this is the concentration of A is equal to concentration A naught minus KT. Once again, these are still the same things. That's our final, that's our initial, that's our rate constant, and that is our time, right? As we go through there. Half-life here is the initial concentration divided by 2K. So much like second order, the initial concentration here plays a role in terms of the half-life. Obviously, if you have a larger initial concentration, that would just mathematically mean that this number is larger and you probably have a larger half-life, right? As opposed to the opposite one. You might have a shorter half-life on the previous one if you have a larger concentration. So it does have an effect on it. Once again here, if we rearrange this as A is equal to minus KT plus A naught, that will give us our Y is equal to MX plus B. And that is what we typically graph, concentration of A versus time here. Giving us our linear relationship. Looks just like the first order one, and also like the first order one, the slope will equal negative of the rate constant. This is actually the graph we saw for first order, but if you graph it for first order concentration versus time, it will not be linear. It will be that decreasing with time graph if it was first order. So although it is the same thing being graphed in both of these graphs, only a zero order reaction will give you that linear relationship when you graph it. If you don't get that linear relationship and get more of the graph like we see on the top there, it's actually going to probably be a first order reaction that's happening in that particular case. So just like the others, the 4 pieces of information, which is important here for zero order: units, rate law, half-life, and typical graph. Any questions on that there? So you can see zero order, second order, and first order, they do have different integrated rate laws and formulas to use. And that's why, again, it's important to figure out what order of reaction you're dealing with, which obviously you could do something like the calculation we did previously using the experimental information to do that. You could also do experiments where you basically do a bunch of experiments and do a bunch of these graphs: first order graphs, second order graphs, zero order graphs, and whichever graph is linear. The most linear will be the order of the reaction. So you could graphically use these things and determine the orders of the reactions. Any questions on that there? All right, so why don't you try one here? This reaction is second order. Okay, so since this is second order, that will tell us that we do want to use the second order rate law here, which is 1 over A is equal to 1 over A naught plus a KT. And we do have our initial, and we do have our final, and we do have our time. So our final here is 1 over 0.001 equal to 1 over 0.01 plus our K, which is what we're looking for. And in this case, our time, I think, is 500 seconds. So here I'm going to take 1 divided by 0.001. I'm then going to subtract it from 1 divided by 0.01. And that's going to give me 900 is equal to K times 500 seconds. And once again, I basically moved that to the other side and subtracted. We're going to divide now our 500 to the other side. Going to give us a rate constant here of 1.8. The units are, I didn't put them in here, but that would be molarity there, and that would be seconds. So that's going to be 1 over molar seconds when I do the division, when it's all said and done in this case. As that obviously is 1 over molar here. Any questions on that calculation? So I would say, again, these are the 3 most common sort of orders of reactions that you come across, as I mentioned, based on just really the number of reactants that are reacting. And most reactions are usually 1 or 2 reactants, which usually leads you to either these things, 0, 1, or second order in most cases. Here's just a table of some of the rate laws and stuff that we talked about for first order, zero order, and second order. And again, usually these 2 things are the most important to know together. If you're good in math, you could also, if you can't remember the half-life equation, you could always substitute in here initial divided by 2 and solve for T as a way that you can get to the half-life equations. As we saw graphically as well, if concentration versus time is linear, then it would be 0 order. If natural log of A versus time gives you that linear line, then it would be first order. And if 1 over A, it would be second order. So again, as I mentioned before, graphically, You can use that to determine whichever line is the straightest. Usually if you do something like graph it in Excel, you can use the R-squared value, right? And R-squared value closer to 1. Linear coefficient there is most linear. All right, the next thing we're going to talk about is the effect of temperature on rates of reactions. And these are two energy diagrams. One on the left is an exothermic reaction. The one on the right is an endothermic reaction. These are our reactants. This is our products. And whenever you see an energy diagram like this, if the reactants are higher in energy than your products, it's going to be exothermic, which means heat and energy is going to be released. In order to get down to the products in terms of energy, energy needs to be given off. Opposite is here. This is our reactants. This is our products. So whenever you have an energy diagram where your reactants are lower in energy than your products, that is an opposite. That's an endothermic reaction. Energy needs to be absorbed or put in, basically, to get those reactants up there. To calculate something like the enthalpy of a reaction or the heat of a reaction, we actually take the difference between the reactants energy and the product's energy, gives us our delta H of the reaction. If you do that, basically your products are lower in energy than your reactants. In this case, gives you a negative number for an exothermic reaction. And if you do the same thing over here, the difference between the energy of your products and your reactants will give you your delta H value for this reaction. Since your products are higher in energy than your reactants, products minus reactants will give you a positive number. So that's what we talked about earlier throughout the semester, that usually a delta H value that is positive will give you a endothermic reaction. Negative is an exothermic reaction because of that. Now, for a reaction to actually take place, there's really two things that has to happen. There has to be collisions between the reactant molecules, and they actually do need to collide with the right amount of energy. So not all collisions, just two things banging into each other, will not necessarily mean that you will make product. They actually has to hit each other in the right spot, kind of like the active site of both of them. And they need to have the right amount of energy. And that minimum amount of energy required for a reaction to take place is what is known as the activation energy. So it's like the hill that the reactants has to climb to get to the other side to make products. And that is this hill right here from where the reactants start to kind of the peak of the hill there. That is your activation energy, abbreviated with E of A. And for our endothermic one, it is here up to here is our activation energy in this particular case. We see that just from the graphs, it is the endothermic reaction that actually has a bigger hill to climb. And that's why it's endothermic, because you got to throw some energy in there to help it along a little bit, right? To sort of gain energy to get up that hill. It also has an effect on the rates of the reaction. The one that probably should be moving faster would be the guy on the left. It has a much smaller hill to climb than the guy on the right. So in terms of rates of reactions, the larger the activation energy, the bigger hill that the reactants has to climb to get to the other side, the slower the reaction. The smaller the activation energy, the faster the reaction can proceed to get to the other side. So what is happening as things progress through a reaction? Hopefully, you know from what we talked about in terms of bonding, you pretty much need to break all these bonds. And then you need to make all these bonds on the other side. So as the reactants start to climb the hill, what's happening is they're starting to break bonds and they're actually starting to make bonds. And what happens when you get to the peak of the hill in terms of energy hill, that is what is sometimes referred to as the transition state. Now, typically in chemistry, if you're really high in energy, is that stable or unstable? Things like to be in low energy. So things that are really high in energy are typically unstable. And you can see in this graph, the top of the hill there is the peak of energy, which means that thing right there is pretty unstable. And it's really unstable because it has bonds that are partially broken and bonds that are partially made. So it's really in, as it says, a transition state. This is what is sometimes referred to as the activated complex. are the transition state complex. And it usually doesn't hang around a very long time. Usually really quickly, it will kind of drop back down the hill to the other side to make your products. So it's usually very hard, a lot of cases, to isolate that guy in the middle because he really doesn't hang around a long time. And that's usually what this little symbol kind of recognizes is sort of a transition state complex. Again, doesn't really stay very, very long. So these type of reactions, temperature obviously plays a role as to how fast the reaction will take place. So if you just think about it logically, regardless of the hill, if you increase the temperature, that gives a greater proportion of reactant molecules that have enough energy to get up and over the hill to the other side. When you lower the temperature, it means that you have a lower amount of reactant molecules that have a sufficient amount of energy to get up the hill to the other side, right? So like when you have a lot of energy, you can walk up and over something really quickly. When you're kind of really low in energy, it's like a whole chore to try to get up and over something. And it works kind of the same way here in terms of temperature. Now, how does a catalyst work? As we talked a little bit about a catalyst earlier, catalyst actually works by finding that alternative pathway for a reaction to take place. And ultimately what a catalyst will do is it will lower this activation energy. So it'll actually lower that activation energy, a catalyst. And that is because it finds, again, an alternative pathway for that to happen, a more efficient sort of pathway for that to happen. And what that does is it lowers the barrier for the reactant molecules, that now there's a greater amount of reactant molecules that will be able to get up and over to the other side because it's a much smaller hill to climb, and they're able to actually do that. The result of that is the rate will actually increase a lot more than it would without the catalyst being present. Any questions on that there? So there is an effect on temperature and the rate, and it's what's known as the Arrhenius equation. This is one version of the equation, and we're going to see probably the more useful version in a second. But these are a couple of things that are the same stuff that we've been talking about. That is the rate constant. That is R, but it actually is the one that has energy, not the one we use for the gas law. So it is this version of R, the 8.314 joules per Kelvin per mole. That is our temperature that does need to be in Kelvin because of this guy being in Kelvin. And that is our activation energy. And usually activation energy is given to you in kilojoules. So usually when you're using the Arrhenius equation, whatever version of it that you use, there's a few different versions of it. You do want to watch units because a lot of times delta H is given to you in kilojoules, R is in joules. So if you do not do that conversion between joules and kilojoules, you're going to be off by a factor of 1,000, which is a very common mistake that people make when they go through it. A is the frequency factor, and it's really the proportion of molecules that have sufficient amount of energy to kind of get up and over that hill to the other side that we're talking about. So it's sort of the proportion of molecules that really do possess that amount of energy to sort of get up and over that hill to make products is what the frequency factor is, which is A in this case. And that's what we talked about, so we won't talk too much about that here. So this is what we see in terms of the Arrhenius equation. And what we see is the rate constant is affected basically by the temperature. So at a lower temperature, we have a smaller rate constant and a slower sort of reaction. But as we increase the temperature, we do see that the rate constant increases. This is actually one version of the Arrhenius equation that we typically use, and this is usually used for graphing. So if you wanted to sort of graph this relationship, this is the one that's typically used. And that is because this is actually also in the form of a straight line. This is y is equal to mx plus b. So a typical Arrhenius plot, you would graph on the y, the natural log of k, which is the rate constant. On the x, you would do 1 over the temperature in Kelvin. And it would actually give you a linear relationship. It will give you a straight line that you could use to figure out something like what the activation energy would be. So that's a very common graphing sort of equation. Let's take a look at it. And that is what we see here. This is, again, our y is equal to mx plus b. And again, on the y, natural log of K. On the x, our 1 over temperature. And if we take the slope of this line, it will actually equal minus E of A over R. So graphically, a lot of times you'll do this type of graph, which is really what part 2 and 3 of the experiment was yesterday when we had the different temperatures. But you would do this type of thing. You would get your points. You would do your straight line. You would get the slope of the line. And from that slope, you could actually calculate the activation energy for that reaction. This is a constant, which is our 8.314 joules per Kelvin per mole. So basically, you just take that number and times it by the slope. Typically speaking, as we see here, this reaction will give you a line that looks very much like this. The slope of that line is positive or negative. Slope of this line is negative, which means your slope value will be negative. And this guy is negative, which means when you calculate the activation energy, it should be a positive number. Because if you look at the energy diagram graphs that we looked at, the hill is a positive hill, right? It's going up. So it's a positive number is what the activation energy should be. But again, R and E of A, you got to be careful of those units because again, they are a factor of 1,000 usually off of each other when you use them. That's basically what that says. Here's what we see graph-wise, again, at a higher temperature, which is the second temperature, are the red graph versus the blue graph. Under the first temperature, this is the activation energy, and this is the proportion of molecules that really have enough energy to get up and over the hill. Not a bad proportion, but we see that if we increase the temperature, we actually get this much proportion of molecules that end up with enough energy to get up and over to the other side. So we could clearly see from this graph that by increasing the temperature, that provides more energy to our reactants. That gives more reactants enough energy to get up and over to the other side. So that is what we talked about earlier, that if we increase the rate of increase the temperature of reaction by like 10 degrees Celsius, you could, in a lot of times, double the rate of reaction. It will occur faster, but it definitely will occur faster if you increase the temperature. And the opposite of that, obviously, if we decrease the temperature, it will occur slower in most cases. So that is the plot and the equation that we've seen. So for example, just to kind of show you how you would use some of that information, if you were given both the rate constant at different temperatures, you would want to do two things. You would want to make sure that your temperature is in Kelvin, which it is in this case. And then really what you would want to do is you would want to take your K values and take the natural log of K of all of them. And that is what you would actually graph again for your Arrhenius plot, which should look like the natural log of K over 1 over our temperature on the X. And again, it will yield you a straight line with a negative slope when you do that. So if we did that to all this information in this chart for this reaction, we will actually end up with a graph that looks something like this. So clearly you would go to something like Excel, punch in the numbers, have it do a best fit line and linear regression, and it will give you this. And from this information, we can use our Arrhenius equation to figure out certain things. We know that the slope of the line is equal to minus E of A over R. We also know that the y-intercept equals the natural log of A. So natural log of A is equal to B, basically. So if we have this equation, this is our y is equal to mx plus B. We can find the activation energy would be minus R times our slope, and that is found from just rearranging this equation, multiplying R to the other side. R in this case is a constant, which is our 8.314. Our slope in this case is negative 1.12 times 10 to the 4. And I should have a negative here as well. And when I do that, I will see that my activation energy for this reaction will be something like 93117 joules, or about 93.1 kilojoules. So graphically, we're able to determine the activation energy from our graph. We could also determine the activation, our frequency factor, which is A. So the natural log of A would equal our y-intercept, which is 26.8 in this case. That would be our y-intercept. A would equal e to the 26.8 in this case, and that would get the e of both sides, basically. And if we did that, that will give us our frequency factor, which again is the proportion of molecules that have enough energy to kind of get up and over. And our A value in this case would be something like 4.36 times 10 to the 11. Now, the units of A are really the same units that we see for K. So in this case, the units of A would actually be 1 over molar seconds. Get back to that page. There we go. Be 1 over molar seconds in this particular case. And that's because when we take the E of both sides, it gets rid of the natural log and just takes us back to basically K, which was our constant there. So this is graphically a very common way that people use to figure out the activation energy of a reaction. It can be done very simply like we were doing yesterday, where you basically do the reaction at different temperatures and you figure out the rate law, you figure out the rate constants, and you do it at those temperatures, and then you can do your Arrhenius plot and figure out your activation energy. Question on that there. Now, most of the time, people really don't want to do graphs of things. So there is a mathematical version of the Arrhenius equation, which is sometimes referred to as the 2-point version of it. And basically what that means is you're going to take 2 points off that line and basically do the calculation rather than doing the graph of all the points on that line. And that version of the equation looks something like this. And there are like 3 different versions of this equation that you could see, depending if they sort of factor out the negative to the outside or combine the denominator there. But this is the natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. These are rate constants at different temperatures. This is our activation energy. That is our R that we've been using, which is our 8.314 joules per Kelvin per mole. And these are our temperatures in Kelvin. Obviously, the rate constants go together with the temperatures. So these are our rate constants at our different temperatures. And we could use this. And this is really like you took 2 points off of that graph and that line, and you can basically calculate it. So if you know a couple of temperatures and a rate constant, you can figure out what the new rate constant would be. Or if you know a couple of rate constants and one of the temperatures, you can figure out what the final temperature would be. So why don't we try one here? So why don't you try to see what you come up with? The reaction has a rate constant 2.57 at 701 and 567 at 895. What is the activation energy in kilojoules per mole? Okay, let's take a look. So we're going to use our 2-point sort of equation here. We do have a rate constant of 2.57. And that goes with a temperature of 701 Kelvin. We have another rate constant that is 567. And that goes with a temperature of 895. We see an increase in the rate constant, by the way, with the temperature increasing, right? Which is what we would expect to happen. In this particular case, it doesn't really matter which ones you call 1s or 2s, as long as you keep the rate constants and the temperatures that go together. In this case, our temperatures are already in Kelvin, so we don't have to do any type of conversion. But again, if they were in degrees Celsius, you would need to do a conversion. And I think that's all we got here. So natural log of K2 over K1 is equal to E of A over R, 1 over T1 minus 1 over T2. So putting in here our natural log of 567 divided by 2.57 equals E of A. Our R is our constant, 8.314 joules per Kelvin per mole. 1 over 701 minus 1 over 895 Kelvin here. So I'm going to clean up this side. You want to actually divide first and then take the natural log, not natural log on both and then divide. So 567 divided by 2.57, and then natural log it. Going to give you, I think, 5.396 equals E of A over 8.314. I'm going to also clean up the parentheses here. 1 divided by 701 minus 1 divided by 895. Going to give us 0.000309215. I'm going to do two things here. I'm going to multiply the 8.314 to that side. I'm also going to divide that number over to the other side, so everybody gets over to the left-hand side there. So we're going to take 5.396 divided by that answer, times it by 8.314, going to give us an E of A when we do that, or an activation energy of 145,084. The units here are joules per mole. And usually activation energy is given in kilojoules, and that would give us about 145 kilojoules. It is a positive number, as you see there, which is what you would expect it to be. It should always be a positive number. Any questions on that there? All right, questions on temperature. So as we see here, temperature will have an effect on the rate. Again, increasing the temperature increases the rate. Lowering the temperature lowers the rate. And again, using something like a catalyst can also increase the rate by lowering the activation.